Let us see yet another version of completeness. We are going to show that the monotone convergence theorem actually implies completeness. So we could have taken the monotone convergence theorem as an axiom instead of the axiom of completeness. Instead of directly showing that the monotone convergence theorem implies completeness, which I am going to cleverly leave to you as an exercise, I will show a theorem that MCT implies AP and MCT implies nested intervals property. Okay, this will together show that the monotone convergence theorem implies completeness by the fact that AP plus NIP implies completeness. Okay, now let's first show that monotone convergence theorem implies the Archimedean property. So what do we have to show? Given x comma y both greater than 0, we have to find n in n such that nx is greater than y. Okay, now suppose not consider the sequence xn equal to nx, right? This sequence is increasing and bounded above. Why? Because y is an upper bound. Okay, by monotone convergence theorem, xn should converge, but it does not because it is not Cauchy. I leave you to check why it is not Cauchy. It's rather easy. Okay, that was really short. The monotone convergence theorem immediately gives the Archimedean property. Now, next, equally easy is the fact that monotone convergence theorem implies the nested intervals property. So, let A and Bn be a sequence or be nested closed intervals. Okay, here again it's very clear, An is an increasing sequence bounded above by B1. Let's say any of the Bn's will actually act as an upper bound. I'm taking it to be B1. Again An converges to some A in R by monotone convergence theorem. But since An is entirely contained in A1 B1, that means A is contained in A1 B1. Similarly, B is contained in A is contained in A2 B2. A is contained in A2 B2 and so on. So A is in fact there in the intersection of A and B. Okay, so I want you to think why A is there in A1 B1 and similarly why A is there in A2 B2. Okay, you can either use the fact that these intervals are closed or use the fact that each one of these ANs have every single Bi as an upper bound. You can use multiple arguments to see that this element A will have to belong to every single A and Bn. Hence we are done. So the monotone convergence theorem actually implies completeness. Many people do take the monotone convergence theorem as the axiom of completeness instead of our usual axiom of completeness. So it is very good to see multiple viewpoints of the same central concept to have a good understanding from multiple angles. Let me leave you in light of this remark with an exercise. Does the Bolzano-Weierstrass theorem That is the fact that any bounded sequence has a convergent subsequence. Does the Bolzano-Weierstrass theorem imply completeness? Of course, the same can be asked. Does it imply the nested intervals property? Does it imply the Archimedean property? Please do think about this. This is a course on real analysis and you have just watched some module on MCT implies completeness.